two-state data types, queues, dynamic arrays and associative arrays, unions and packed structures, classes and structures, strings and enumerated types. So we will discuss one by one. So coming to two-state data types, it will offer us better performance, reduced memory usage, and queues, dynamic arrays and associative arrays, and for automatic storage, and for reduced memory usage, built-in support for searching and sorting. And coming to unions and packet structures, allows multiple views of the same data, and classes and structures support for abstract data structures, and strings are for built-in support, string support, and enumerated types. They help for make the work code easier and easy to understand. Wait a minute. So let's start our two-state data types. So before starting with the two-state data types, so in Verilog we have reg and var, right? So this reg or var, can anyone tell how many values this reg and var can store? What are the values? These are the values, right? Reg and var can store these values. Am I right? So reg or var can store 0, 1, unknown and high impedance. So this reg and var can go into 0 state or 1, or it can also go into unknown state or an high impedance state. So how many values we have here? 4 values. So in Verilog we have 4 state data. So these are called states. 0 is one state, 1 is one state, unknown is one state, and Z is another state. So in Verilog we have only 4 state data types. We don't have any 2 state data types in Verilog. But System Verilog introduces a concept called 2 state data types. That is, we have only 2 states. 2 state data type. What are the what are those two states? One is 0 and another is 1. So we don't have unknown and high impedance for this two state data type. So remember this is a very important point which is also asked in interviews. What is meant by a two state data type? So two state data type is nothing but which can only have two states. One is 0 and another is 1. So in System Verilog we have two state data types which can have only 0 and 1. And if we want to and if we try to assign any other value other than these two states to this data type, then it will convert those values into 0 or 1. For example, if a variable a is of two state data type, say suppose bit is a two state data type, and if we declare variable a as bit, so a becomes a two state data type. And if we want to try to assign a is equal to unknown, then the simulator will convert this unknown value to any of these states, that is 0 or 1. So this is how a two state data type works. So is this clear about two state data type? What is meant by two state data type? This is clear, right?
Yeah, yes.
So Verilog has two basic data types, reg and nets, that can hold four values: 0, 1, 0, 1, x, z. So Verilog can hold these four values. So this is called a four state data type. Regs and wires are called four state data types. This is a very important question, and the first question which is asked in many of the interviews, like what is the difference between a four state data type and two state data type. So you can answer accordingly. So coming to System Verilog, we have been introduced to two-state data types. So before going into two-state data types, we will first discuss about logic data types in System Verilog, which is a four-state data type. So System Verilog also introduced a new data type called logic. This is a new data type which is introduced in the System Verilog, which is a logic data type. So this is also a four state data type. Remember this. This is a four state data type. This means it can store 0, 1, X and unknown. This is similar to reg and wire. So logic is a new data type which is introduced in the system Verilog, and it is a four state data type, and it can hold 0, 1, xz. So that's why it is a four state data type, and this is similar to reg and wire. So, but why this logic data type has been introduced if we have reg and wire in uh, Verilog? Why we need a logic data type in system? Let us consider a example, module example, and say if we have input AB and output C, and we have not discussed this procedural and continuous assignment. We have discussed in Verilog about continuous assignments, but we haven't discussed about procedural assignments. For now, just remember that initial begin block is a procedural statement and assign is a continuous statement. We have discussed about this continuous assignments. Assign is a continuous assignment. We have discussed in data flow modeling. We will discuss about this initial begin and always begin in upcoming sessions. So for now, this initial begin is a procedural statement, and this assign is a continuous statement. So in procedural statements, we can assign the value, we can only use reg type, reg data type. So if I declare another output as reg d, okay, so yeah. So in procedural statements, we can use only reg type. We cannot use wire type. We will get an error if we use wire type in procedural statements. For suppose I cannot make C is equal to A plus B in the initial beginning block, it will throw an error because by default output is a wire. So we cannot use wire, but I can use D is equal to A plus B since I am declaring D as a reg type. Okay, and coming to continuous assignment statements, I can use only wire types. We are seeing in data flow modeling, right? We can use only wire types in with assign, but I cannot use reg type with assign. So here I cannot use assign D is equal to A plus B. This will throw an error. I can use only assign C is equal to A plus B since C is an wire type. So I can use this statement. So what's happening here is we will sometimes in hurry we will declare input a comma b and output c like that, and we will uh, write the code, and after compiling it we will get errors, and we will then come here again and we will make this out c as reg, and if we make C as reg, then it will work here. But this C will not work in the continuous assignment. If C is a reg type, then it will work in the procedural statement, but it will not work in the continuous assignment statement. Then we have to, for making it to work, then we will declare some internal registers and we will assign it to the C like that. So so to avoid this all confusions and lengthy processes, system Verilog introduces a new data type called logic data type. So if we declare any variable with this logic data type, say logic C, then this C can be used with any statements, like it can be used with continuous assignment statement and procedural assignments also. That is, if here I am declaring output C as a logic, so if I am declaring output logic C, then the C can be used here procedural statement as well as continuous assignment statements. But we cannot use C in both the statements at a time. It will throw an unknown value. If But we can use C either in procedural statements or continuous assignment statements. if we declare C as a logic data type. So this is the use case of logic data type. So is this clear for everyone? This is clear? Any doubt?
Yeah, yeah.
If you have any doubt, please ask guys so that I can know whether you are understanding or not. So with the help of logic data type, we can use the variable within a procedural statements or continuous assignment statements. So the one thing in Verilog that always leave new users scratching their heads in difference between a reg and while. So system Verilog improves the classic grid data type so that it can be driven by a continuous assignment gates and modules. In addition to being a variable, it is given the new name logic so that it does not look like a register declaration. The one limitation is that a logic variable cannot be driven for multiple drivers, such as when you are modeling bidirectional bus. In this case, the variables need to be net such as well. This we will discuss in our future sessions. What is this? And we will discuss about this point. So finally, this when we declare any variable with logic data type, it can be declared. It can be used both in procedural statements as well as continuous assignment statements. So this is clear, right? About logic data type. This is very important data type. If you have any doubt, please clear it now. So is this clear? Can we move forward? So we will see an example of this logic data type by coding also in our further sessions. So for now, just remember the how we are using this logic data type. Now, next coming to two-state data types. As already discussed, in case of two-state data types, we have only the two-state data types can only take two states, that is 0 and 1. So System Verilog introduced several two-state data types to improve simulator performance and reduce memory usage over four-state data types. So in two-state data types, we have bit data type, byte data type, and we have int. Also we have short int, long int, and long int. So please remember that these are two-state data types. Two-state data types. That is, they can only take the values of 0 and 1. They cannot take the values of x and high impedance. If we try to assign these values also, the simulator will convert those values into 0 or 1. So these are the two-state data types: bit, byte, int, short int, and long int. So the simplest type is the bit, which is always unsigned. Yeah, we will discuss about one by one. So coming to bit, so if we declare any variable of type bit, then it will be of bit data type. So this has only two states, either 0 or 1. If we declare bit b, then we can either store 0 or 1. And this is unsigned. That is, we can only represent positive numbers. We cannot represent negative numbers using this bit. So this is also a very important point. Wait a minute, let me add some more slides. So interviewer may ask many, they can frame many questions from this particular slide only. So please listen it carefully, and if you have any particular doubt, you can clarify it now. So coming to bit data type, this is a two-state data type, and it can only have the values of 0 or 1, and this is unsigned. Remember this, this is unsigned. We can only represent positive numbers using the bit data type. Yeah, these are the 3 points to be remembered carefully. So if we declare bit B, then it is a two-state and single bit. And we can also declare, for example, bit 5 down to 0, A. So A will be of bit data type, and the width of A is 6 bits. 1, 2, 3, 4, 5. So this A can store 6 bits like this. So the width of, sorry, this is not an array. Uh, the width of the A is 6 bits. That is, A consists of 6 bits, and it can have only the values of 0 and 1, and it is unsigned. If we use bit data type, then we can only represent positive numbers. We cannot represent negative numbers using a bit data type. So coming to int data type. So this, it is also a two-state data type. And the size of this int data type is 32 bits. And we cannot store unknown and high impedance value in this int data type. And this is also unsigned. Sorry, this is signed, and it is 32 bit. This is signed. That is, we can store negative numbers also in this int data type. So this int data type is of two state. This is two-state data type. That is, it can store 0 and 1. It cannot store unknown and high impedance values. And the default size of this int data type is 32 bits, and it is signed. That is, we can store negative values also in this int. So for example, if we declare int A, so what is the size of A? It is 32 bits, and this is signed. That is, we can assign A is equal to -4, A is equal to +4, like this. We can store negative and positive numbers in this using this int data type. So remember this. And in this int also, we have short int and long int. So we have short int. This is a 16-bit data type, and coming to long int, it is 64-bit, and normal int is 32-bit. So remember these three types of int data types in system Verilog, and these are all two-state data types. Two-state data types. So is this clear for everyone?
Yes.
And coming to byte data type, we have also another data type called byte. So this is also a two-state data type. That is, it can store zeros and ones, and this is a signed data type. So byte is a signed data type, and byte is nothing but the default size. The size of byte is 8 bits. You know that 8 bits is equal to 1 byte, but this byte data type is a signed data type. Remember this point. This is a very important point. So byte data type is a signed data type that is, it can store negative values also. For example, if we declare any variable as byte, say byte m, then we can store negative values in this m, since it is a signed data type. So the size of this m is 8 bits. So can anyone tell what is the range we can store in this byte data type?
8 bits.
Yeah, like what is the range?
7.0. 0 to 7
Uh,
means 0 to 255.
yeah, so we, we will answer 0 to 255, but this will be the wrong answer because it is a signed data type. It can store negative values also.
0 to 127.
It will be -127 to +127. since we can store negative values also, so this will be included minus 127. So here we should be careful because it is a signed data type, so we can represent negative values also. This will also be covered. So is this clear? So because it is a signed data type, we can we can represent from minus 127 to plus 127. Generally, we will give the answer from 0 to 255, but since it is a signed data type, we can represent from minus 127 to plus 127. Give me a minute. Let's see an example here. If we have bit 7 down to 0A and byte A. So how many bits we have here?
8.
8. And how many bits we have here? 8 bits.
8.
So what is the range in the first case? 0 to 255. Since it is an unsigned number, we cannot represent negative numbers in this representation. And what is the range here?
Minus 127 to 127.
So this is the point
We-
interviewer asks.
Only in the case of bit we use unsigned numbers. Remaining all the case we use signed numbers, right?
Yeah, bit is a unsigned representation. So by default in system Verilog, bit is unsigned type and byte is signed type.
And int, short int, long int, they also
Int is also
separate.
int is also signed.
Short int. What about short
Yeah,
int and long int?
all int types are all signed types.
Signed.
Yeah.
Okay.
So this is a point interviewer expects the answer in this form. Like what is the difference between the bit and byte? So we should tell him that in case of bit, it is an unsigned representation and the representation is from 0 to 255. Whereas with byte, we can represent from minus 127 to plus 127. And so if we should be careful while coding also, in if there is a scenario like we want to represent bit 7 down to 0a, so instead of writing bit 7 down to 0a, I will write simply byte a. Then we will think that there is no difference between these two, but there is a lot of difference between these two because bit is an unsigned and byte is a signed, so the results may be different in both the cases. So this is what this is the point we should be careful. So is this clear for everyone? Shall we move forward? Is this clear, right?
Yes.
And coming to short int, it is a two state 16-bit signed integer, and coming to long int, it is a two state 64-bit signed integer. So these are the two state data types, and be careful connecting two state variables to the design under test, especially it outputs if the hardware tries to drive x or z values. Yeah, so in by using system Verilog, we are basically writing the test bench, right? So if this test bench is connected to a design and we are collecting the outputs by using this test bench and we are collecting it into a two-state data type, if we are collecting the outputs of the design into a two-state data type, and if the design throws x or high impedance values, and if we are trying to store this in our two-state data type, then the simulator will convert this x or z values to 0 and 1. So we will not know whether our design has given x or z values if we use two-state data type. So we should be careful when we are collecting outputs from our design into this two-state data types. We should, so in these cases, we should be careful. So these are about the two-state data types in system Verilog. So remember these points, remember the difference between the bit and byte, and do remember whether the particular data type is a signed or unsigned. This is very, very important point to be remembered. This signed and unsigned makes a lot of difference here. And remember the how logic data type is being used in the system Verilog. So we will in system Verilog we will use only logic data type most in most of the cases. And now coming to fixed size arrays. So the representation of fixed size arrays can be of two types. Let's say I will take int type int a. A minute. I will take int a of so if we have a variable a of int type, and if I want to declare an array, I can declare like this 4 down to 0. So this is one type of representation, that is an array will be created of 5 locations 1 2 3 4 5 1 2 3 4 5. Each location consists of a data type of int. So there are 5 locations present here, and we can also represent int a of 5 simply. So this is another type of representation. No need to represent 4 down to 0 or 0 down to 4. System Verilog gives us flexibility to represent the arrays like this. Int a of 5, so it will create a array of 5 locations. And if we want to assign any value to any of the location, we can write a of 4 is equal to 1 or a of 3 is equal to 1. This is how we can declare a fixed size array. This is a fixed size array, and we can create an array and we can assign the values to these arrays. And the size of the array must be a constant expression known at the compile time. So the size of the array must be known at the compile time in case of fixed size arrays. And these are the types of fixed size arrays. We can declare logic type, bit type, and byte type, int type, shorthand type, real type. So we are just mentioning the data types here. This is the syntax of arrays. And if we, for example, say logic 2 down to 0, a of 3. So can anyone tell what is this means? What this means? So how many locations we have? So we have 3 locations. And what is the width of each location?
1 bit. 3 bits.
So we have 3 locations and width of each location is 3 bits. And what is the type of the array? Logic type. So this is how a fixed size array looks like. And we can also take bit 7 down to 0, a of 10. So we have 10 locations and each location is of 8-bit width, and the data type of this is bit. So this is how we declare the arrays. So is this clear, right, about fixed size arrays? Can we move forward? Hello? And we can also declare multi-dimensional arrays. In Verilog, multi-dimensional arrays is not possible, but here we can also declare multi-dimensional arrays, that is 2D arrays. The syntax is very simple. Int a of 3, this is first dimension, followed by second dimension. So in first dimension there are 3 locations, and in second dimension we have 4 locations. So this is a multi-dimensional array of type int. And here if I declare a of int a of,
Hello.
yeah.
So then how we declare that multi-dimensional if my design is having such functionality? So how I will be declaring in my design if Verilog doesn't support this?
So we will not use multi-dimensional arrays in the design. It is not, we cannot synthesize any hardware. So this is only for testing purpose. We will not synthesize any hardware.
Okay.
So practically we cannot synthesize a multi-dimensional array on a hardware. So it is not possible. This is only for simulation purpose.
Okay.
Yeah. So if we have a fixed array, so remember this, in case of fixed array, we are mentioning the size of the array. This is a fixed array. Since I'm mentioning the size before only. Wait a minute beyond that. So this is about multi-dimensional array, and if we want, yeah, and we have another category called unpacked arrays. Till now we are discussing about this unpacked arrays only, but I have not used this term. So unpacked array syntax will look like this: bit a 4 down to 0. We are giving the number of locations after the variable name. We are giving the size after the variable name. So this is an unpacked array. So in case of unpacked arrays, so this is an unpacked array. If the size is represented after the variable name, then this is an unpacked array. If size is declared before the variable name, then this is a packed array. Remember this is a very important difference between the packed and unpacked array. In case of unpacked arrays, the size is declared after the array name, whereas in case of packed arrays, the size is declared before the array name. So this is the difference between the packed and unpacked arrays. So unpacked arrays will look like this. So if we declare a bit a 4 down to 0, so uh, our unpacked array look like this with 5 locations: 3, 4, 5. So this is 1, 2, 3, 4, 5. Each location has 1 bit. Whereas if we declare bit 3 down to 0, a of 4 down to 0, that is, we have 5 locations: 1, 2, 3, 4, 5, and each location is of 3 bit size. Each location is of 3 bit, and we have 5 locations. Here what's happening is we are simply seeing this 1 bit location only, but simulator will create still 31 bits. So it will create a 32-bit boundary for each location. So each location actually consists of 32 bits, but here in this case we are declaring bit a4 down to 0. So each location has only 1 bit. So this 31 bits will be unused. So in this diagram we can see this is unused space. So simulator will create 4 bytes of memory for each location. But if we are using only say suppose in this example we are declaring only bit a 4 down to 0, we are using only 1 bit. We are storing only 1 bit in each location. So remaining 31 bits are unused. And here in this case we are using bit 3 down to 0, a 4 down to 0. That is, we are creating 5 locations, and each location we are storing only 4 bits of data, and remaining bits and remaining are unused. So this is the meaning of unpacked arrays. For example, if we use bit 31 down to 0, a of 4 down to 0, then we are declaring 5 locations, and we are storing 32 bits in each location. That is, we are completely using that location. So this is how we represent when we declare an unpacked arrays. So here we can see we are declaring bit 7 down to 0, b underscore unpacked of 3. So 3 locations will be created, and 32 bits will be created for each location, but we are using only 8 bits here. We are storing only 8 bits, so remaining are unused in case of unpacked array. So is this clear, right? Is this clear for everyone? This is a very important point to be remembered. So is this clear?